first line. So yeah, don't be shy and move to the front. Okay, it's time. So let me start MAE seminar. Hello everyone. It's my pleasure to host Dr. Özel in MAE seminar. Dr. Özel is a full professor in the Department of Industrial and System Engineering and the Director of Manufacturing and Automation Research Lab at Locust University. He received his PhD in 1998 from Ohio State. And he's a really very active researcher in the area of advanced manufacturing, modeling, machine learning, and additive manufacturing, and funded by various government agencies, NSF, DOD, and also by industries. Today, Dr. Özel will give us a talk about his visionary research on smart manufacturing in metal additive manufacturing. Okay, let's welcome Dr. Özel.
Thank you, Professor. Good morning, everybody. Thanks for coming this Friday morning to this talk. This talk is about a plethora of things that I've got involved in metal additive manufacturing. So it involves process monitoring and modeling techniques and for quality of those products made by metal additive manufacturing, but also talks about digital twin for metal additive manufacturing. So digital twin, probably you keep hearing about it, is a concept introduced in many years ago, and it is actually quite old because it started at NASA. You know, when you make things, you keep a digital copy of it. But the idea is that you have a physical system, and you're very familiar with the physical systems, like a machine tool is a physical system. And then you have a digital model of the system. And then the data flows from the physical system to the digital model. And then through analytics, the data can be processed in a way that goes through the models and then is fed back to improve your physical system. To be able to actually implement that, you need actuators that are controlled by your digital system, as well as sensors that collects data. So this is from, I think, Siemens, and Siemens is really big in implementing digital twin. And let's look at digital twin and where it is and where it will be. This is a very famous Gartner hype cycle. So along the hype cycle, the idea is right. So the first stage is the innovation trigger when you start hearing about new things. And then they build lots of expectations. And those expectations are actually inflated. And it reaches to the peak inflated expectation. And then there is the realization. It just drops from there and then settles to a plateau of productivity when it's implemented. So digital twin at the time, 2020, just passed the peak of inflated expectations. So it means that it's quite happening. And so it's expected to be in mainstream adoption within 2 to 5 years. And obviously that estimate is a very rough estimate. So we're in 2022, moving forward 2025 and onward, you will see more of the digital twin in the companies. They will be talking about it. So let's give some definitions. Digital twin is essentially a comprehensive physical and functional description of a component, product or a system, which includes all information which could be useful in all life cycle phases. And so again, digital twin is actually through the digital transformation, taking a physical system in the paradigm. You probably heard about metaverse, but think about something similar metaverse in industrial system. So obviously companies are taking on that, and you will see more and more companies like ANSYS, AutoCAD, Dassault, and computer-aided engineering software will actually try to produce products similar to this. When you look at the definition, digital twin and digital twin prototype, which means that you have the physical product and a prototype product. And in this case, you could create the physical twin and digital twin of that. And digital twin instance rather, is a preset moving forward to a concept digital thread, which means that in time, the physical system changes. Like when you buy a new machine tool, it performs very well, but after a while, it needs an adjustment calibration. And then through time scale, you can look at the digital twin instances, and you can record those instances. This is good for the life cycle analysis. And that's what the definition of digital twin instance. When you sum up all those digital instances throughout the time, you get digital twin aggregate. And it's the combination of those digital twin instances. And then you have the digital twin environment. All those digital twins are, in a way, popping up and learning from each other. But then the digital thread would be essentially looking at the life cycle of those digital twin instances and recording from the beginning and to the end of a life cycle of a product, digital instances, that's digital thread, and you archive it. I don't know if you heard the Apollo mission, right? So we're trying to go back to the moon again, but we can't. Why? Because we lost most of the information about the Apollo mission. And because there was no digital thread, no record of the entire experience. So you can think about it that way. It's very important. So let's just go through some of the basic concepts, because digital twin is too much of a jump, because to be able to get there, you have to take some steps. First, let's give a definition of the digital model. Digital model is something that you've been doing all the time. Do you do simulation models? Yes, right? You simulate something in ANSYS, you write a MATLAB code, simulate control system or something. That is a digital model. But which means that digital object does not communicate with the physical object. There is only manual data flow, which means that you take the digital simulation results and use it the way you want in your physical system. The next step is digital shadow, when you start hooking up some sensors, and you do that, visiting your labs, some sensors to the physical system. Then, if you connect those sensory data to your simulation model or digital model, you have an automated data flow between the physical object and digital object. And then you assess it through the data analytics, and then you decide how to improve your design. Like you're designing a aircraft wing, and you put a lot of sensors, you collect data, look at the flow, and then you can change the design. That is a digital shadow. So the digital twin means that when you have full connection between the physical object and the digital object, and the data flow is fully automated, and then obviously the intelligence, the autonomous aspect of it will come from machine learning, right? The system will learn, the digital object will learn from physical object and make a whole bunch of simulations, and the results are going to be autonomously fed to the physical object. This could be like an aircraft. So if you have a digital twin of an aircraft, you create it in this space, metaverse, and then you can actually make all the changes to the aircraft digitally, see how it performs, and then you finalize your design. And just like 3D printing, before, people didn't think that you can just, a computer model can be push of a button, be realized in a 3D printer. Imagine you have a product you design in the virtual world, and once you're satisfied with a push of a button, you will actually manufacture it. So it will happen, we don't know, but we're working towards this because we're engineers. We've been doing design and simulations for years. So this is like a historical look at evolution of engineering design. If you look at the computers when it came out, IBM mainframe, 1960s, it actually changed everything. So that was the first steps of computer-aided engineering, correct? And then as a result of that, we were able to do computer-driven design. And then between 1985 to 1999, we have a new activity, simulation analysis application. This is when I was a student. And then there were packages like Abacus, Ideas, many like T-Form we use for metal forming simulations. Then from 2000 to 2014, these simulations became so routine practice, right? So today you teach your students, you project, do structural analysis, do thermal modeling, thermal analysis, find temperature distribution, find stress distribution. They can do it on a fly. Right, so it became simulation-driven design. So in companies, they do that every day as a routine job. But now what's the next step? From 2015 to 2021, or 2023 right now we're in, is the digital models, evolving into digital shadow, digital twin, and digital thread. Now you know the definitions. Digital thread is the entire life cycle recorded digitally of a product from the design and from the take back, you end the product. And digital twin is essentially all the, throughout the life cycle of the product is the digital shadows are connected autonomously to the system. So you see here, this is a kind of image. I like it very much, an engineer wearing mixed augmented reality goggles and looking at a turbine engine. And the turbine engine, there are lots of turbine engines I saw today. They don't move, they don't operate. But if you actually wear that, you will be able to see, you can operate in the digital space. It's like a metaverse, right? Metaverse of your engineering object. This is where the things are headed. And you can just learn about that more by looking at, companies' websites, or like a good place to learn from is also Deloitte. Deloitte, issues a lot of reports for technology. So here is digital twin in metal additive manufacturing. So we have lots of simulations that we're doing. Here's some simulations I picked from Materialize. It's a Belgian company about the displacements of the part. Here's another one showing the total displacement. This is about topology optimization. So digital twins method can be used in metal AM, and it can help to reduce the production cycle time because you can virtually design the product and also set its manufacturing parameters and optimize its manufacturing parameters, and to reduce the number of defects you will get because it's not just simulating, the displacement or the, stress analysis or thermal analysis. You may be able to actually improve it so that you can actually predict the microstructure, pores, defects, and other things as you improve your digital models and towards the digital twin. And then eventually increasing the quality of the products. So it will actually create a revolution when everything happens. So digital twins, in this case, we're talking about just simulation models, digital models. In that case, also can help in forecasting the temperature, velocity, displacement, cooling rates, and solidification parameters of the models. All the things that you're learning in your classes, solid mechanics, fluid mechanics, thermodynamics, and other metal forming and manufacturing processes courses. So if you look at the challenges in metal AM, where metal AM was able to penetrate the most, you can see that it's already penetrated in some industries like aerospace and automotive industrial machines, medical and dental fields. So it is penetrating in several industrial applications as a new way of manufacturing, remanufacturing, and repairing parts and products in order to optimize their life cycle. So it is a disruptive technology, and many challenges, however, still exist because a lot of scrap parts are also made with metal AM. Not as much as CNC machining, because CNC machining is a more mature technology. So you can actually minimize scrap, minimize inventories, minimize the carbon footprint, and manufacture first time right by addressing those challenges. So also metal AM somewhat falls short on fulfilling those high expectations. So remember the Gartner's hype cycle. And now it's becoming more like a real revolution and a disruptive technology. However, there's still a lot of high expectations that are not fulfilled. And the future for the digital manufacturing is limited because of the lack of knowledge about the process and lack of robustness in the sustainable value chains through using metal AM. So it's important to generate new knowledge, but also not lose the conventional knowledge in material science, process planning, post-processing and control, heat treatments, and also new way of training and education in this field is required. So let's talk about some of the metal additive manufacturing technologies. The first one is the powder bed fusion. In the case of powder bed fusion, is the feedstock is powder metal and uses an energy source to create a melt pool. And this energy source could be lasers or electron beams. So we have an energy source, right? So, and then the feedstock is powder. And then we can have heat energy generated with it. And then we can use a laser beam, and then it's the powder laser beam powder bed fusion. Or we can actually have an electron beam. In this case, we can have powder electron beam powder bed fusion process. And then you can see the share of those two powder bed fusion processes amount to 54% of all the metal additive manufacturing. So this is the big group of metal additive manufacturing technique. And then the others, you can see directed energy deposition, either by using laser powder or wire arc, and binder jetting. Just today, I saw in your lab that you were using a binder jetter, right? Okay, so powder polymer extrusion, and also because the powder metal is maybe encapsulated inside the polymer. And then there is others. So if you look at the directed energy deposition, that's the second group, but it's also growing faster. The reason that it didn't grow as fast as the powder bed fusion can produce very accurate parts. It's done in a controlled chamber. Directed energy deposition more in the open space and has lower accuracy. In this case, you can have a number of energy sources that you can utilize. One of them is just like the powder bed fusion, you can utilize heat energy. And then if you utilize laser beam, just like the powder bed fusion, you end up with laser powder directed energy deposition, or you can use wire as the feedstock, then it becomes laser wire directed energy deposition. If you use electron beam as the energy source to generate the heat energy, you can have wire electron beam directed energy deposition. And then if you use a plasma as the heat energy generation source, you can have wire plasma wire directed energy deposition. If you use electrical arc, this is a lot easier because you have a lot of experience with arc welding. Then you have wire wire arc-directed energy deposition. So that's more like a general terms to describe those type of directed energy deposition-based additive manufacturing processes. There's also solid-state directed energy deposition happening, and these processes utilize other energy sources like kinetic energy, ultra-high speed. Powders are accelerated, and they are deposited onto a surface, just like laser cladding, but in this case, just like cladding, I should say. In this case, it's actually being sprayed, so it's called powder cold spray. And that's in that others group. And you can see the share of directed energy deposition. So we have done research in a lot of those processes, so I'm going to go through them a little bit and give you an idea about. So laser powder bed fusion is oftentimes done in a environment where you utilize a fiber laser, and it goes through focal lenses and then a scanner head that has a theta lens and moving mirrors, and then reflects the laser beam onto powder bed, and then actually locally melts, create a melt pool, and then melt pool moves in order to fuse the powder metal together. And it is important to define one parameter. Here is the energy density. This is volumetric energy density. Laser power is divided by the scan velocity, hatch distance, and the layer thickness. As a result of that, you get joules per millimeter cube type of energy density. Now, if this energy density is at relatively low levels, then the induced heat is rather low, and powder particles are melted without evaporation. So laser energy is absorbed by the upper surface of the powder material and resulting in a shallow melt pool, and this would be called a conduction mode laser powder bed fusion. If this laser-induced energy density is higher, in that case, if it exceeds a certain value, what value it could exceed? Latent heat for evaporation, right? You learned this in the heat transfer. And then that is the evaporation that takes place. In that case, there is formation of a keyhole, and then this is a convection mode, and then keyhole can penetrate deep into the material in the shape of a keyhole cone geometry. So let's look at the type of defects that you can get in the laser powder bed fusion. So you can get defects such as, the cracks, surface recesses, keyhole, porosity, spatter powder, ridge-like fused track lines. And so you see the track lines. The track is moving this way, track is moving that way, reversing direction, moving back and forth. And then these are the melt pool fronts. So it leaves literally those marks. Just like milling marks, you see milling tool cutting and then leaving milling marks. But also it leaves a lot of defects, and that's the problem. That is the barrier for metal AM to move forward. And so this is from our latest review paper. And this is a very crowded slide, but that you can also see the each of those defects, what are their causes, and what is the effect on quality. And people have been studying those for the last decade, literally, and trying to understand. So you have porosity, lack of fusion, cracks, residual stresses, bowling, keyholing, geometric distortions, layer delamination, and surface defects. All of the causes pretty much associated with the process. So, and if you can understand the process through the simulation models and through monitoring the process, then you can actually maybe control and predict the quality and control the process. Let's kind of review what are the process monitoring methods and their stages used in additive manufacturing, metal additive manufacturing. The first one shows two ways to do that: on-axis or off-axis detection. So off-axis detection would be that you could actually stick a microphone or an acoustic sensor or a camera to look at the melt pool from the side. not through the laser beam axis. On axis means that you look at the process through the laser beam. So you're actually trying to monitor the melt pole in this case. Off-axis monitoring of the melt pole can be done by using optical tomography. In this case, you see that there's an off-axis camera, and that camera is not just a regular camera, it's a special camera like an IR camera, thermal vision camera, or it's a high frame rate camera that can actually collect thousands of frames per second so that you can actually dynamically see how melt pole is moving. Or you can just do on-axis monitoring melt pole by using optical tomography. In this case, you have to be very good in optics and also lasers in order to separate those views from the melt pole, because you have a laser scanner, you have f-theta lenses, but the radiation coming back from the melt pole is picked up by these sensors, photodiodes that can be used. There's either single or two color photodiodes can be used. Anyway, so to summarize, the types of monitoring methods can be applied, not just the on-axis, off-axis, by using cameras, CCD or CMOS cameras, or infrared or near-infrared cameras, pyrometry, or fringe projection, or line scanner, or optical tomography. We can actually look at the parameter that we would like to monitor. So here you see melt pole we're trying to monitor. And then we have powder spreading and deposition we can monitor, because in the powder bed fusion, it's important that the powder is laid uniformly and with a high quality. If you have defects on the surface, you're laying another layer of powder. The new layer of powder is going to incur all the imperfections, roughness on the surface, and it's going to collaterally create defects, right? So you will be able to, using fringe projection, using line scanner, look at the spread. So there are many different methods can be applied to generate, and this is also important for our digital twin. Remember, we said that we want to collect through the sensors as much information as we want from the physical object. Here is our opportunity to do that. So are there any machines that utilize all of those monitoring methods? No. So, but, different approaches for different purposes. For example, we also will classify monitoring stages in-situ process, ex-situ process, post-process. So the in-situ process is essentially when the process actually takes place, in-situ in-process monitoring. And that's important to see the health of the melt pole. Is it conduction mode, convection mode, or mixed mode, keyhole? Can we actually monitor that? The ex-situ method is essentially when we are actually preparing in-situ process, right? For example, spreading the powder, or a layer is printed and we would like to see the roughness on the surface. The surface topography analysis in ex-situ. Post-process meaning that part is built, you blow the powder and you took the part out. Now you're looking at the part. You're looking at the microstructure, surface roughness, and so forth. So, and that's also considered, defect analysis, looking at defects on layers. So, what kind of classifications we can actually talk about as in-situ sensing and monitoring methods? At the lowest level, level 0, we can actually use existing signals in the machine. Because machine is actually giving a lot of temperature, you can read it from the machine very easily. Statistical machine learning to predict the defects onsets. What changes in the machine that creates onset of those defects that occur, right? Can we characterize those existing signals to predict the defects, onsets? The second level is essentially level 1. This looks like, when you go to an airport, like level 0, level 1. But, level 1 is monitoring the powder bed using high-resolution images, and then you can identify possible defects, possible to detect the lamination defects, and then look at the geometrical deviations between the actual and nominal shape, layer by layer, And there's none of that right now. So you don't know the geometry. Is the building three-dimensional, right or wrong? How? Because the three-dimensional build is inside the powder bed. You cannot see it. If you use XCT, computer tomography or something like that, you can only see it. But that's so expensive at the moment. So it requires new techniques to be developed to be able to see this in the level 1. Level 2, monitor printed layer, which means that every time you fabricate a layer or every 10 layers, you can look at it and then take those images, use through the deep learning and characterize whether this is actually going to result in high quality or low quality of parts with defects, which means quality prediction. So at this moment, you can do quality prediction. At the level 3, you can monitor tracks, which means like, a part is actually split to geometry stripes. The stripes are split to tracks, and this is how the laser powder bed fusion works. So you can actually look at the health of the track. What is the process signature track to track and stripe to stripe? So you can look at the transition of quality states at this level and look at evaluate the spatter signature, evaluate the solidification cooling, look at the cooling rates. You can measure them, and I'm going to show you some results. And then level 4 is the top level, and it gets smaller and smaller. Right now, you're just only looking at the malpole. And then you have malpole model, simulation model. You can continuously merge your digital model with the physical monitoring signal. So let's look at the mapping between those process signatures and methods. We can also actually look into level of monitoring. We talked about level 1, 2, 3, and then process signature and size, shape, average density, powder bed homogeneity, slice geometry, slice surface pattern, and so on. And then look at what is the current status, how strong, what is the degree of known relationship demonstrated in the literature, while the other symbol is used to represent the degree of link still not strengthened in the literature, or there is really some potential is not being explored yet. So these are the first table. Remember, porosity, cracks, residual stresses, layer delamination, grain, anisotropy, balling and keyhole, geometric distortions, and so forth. We can look at the mapping between the process signatures, defects, as well as level of monitoring can be utilized. Let's look at the commercially available laser powder bed fusion systems and their in-situ monitoring capabilities. So for the direct metal printing, manufacturers the 3D systems, they use optical for the powder bed, malpole for optical for malpole and spatter, and for the defects, lump formation, metal powder bed fusion, and Renishaw, selective laser melting, SLM solutions, direct metal laser melting. They're all powder bed fusion processes, but they cannot call them powder bed fusion because it's a trademark name. They have to pick something different to uniquely call their product. And then you can see that they're utilizing to a certain degree all those process monitoring systems. Well, now let's get some of our research results. Let's give an example for in-situ analysis. That is a digital shadow. So we collaborate with the NIST, National Institute of Standards Technology. They have a powder bed fusion machine, a laser powder bed fusion machine equipped with high frame rate camera, as well as a thermal camera to look at, this is like track processing, track to track. And this is a stripe. Stripe is like a long band, like a ribbon. And then the tracks are being followed in order to fuse the tracks, powder material track to track. Then the stripes are fused with the stripe overlap. And then the process parameters there is the essentially scan speed, hatch distance between the two tracks, as well as the stripe width. And obviously, this is local thermal processing, and it's going to result in some kind of anomalies you can call, and as a result, defects. If you were to monitor the malpole, and this is just the high frame rate, grayscale, image, and we can use digital image correlation to separate regions by essentially converting the grayscale intensities to color codes. We can identify the melt pool shape, spatter, and the vicinity of the melt pool. And then we can quantify the melt pool area, and we can actually look at statistically how the melt pool dynamic is changing. Through the thermal imaging, we can actually look at the thermal original image and clean the glare in the lens, and also apply machine learning to actually convert the shape analysis. We can actually find the amount of spatter is taking place in this case. So this is a thermal camera result. Through machine learning, we can actually obtain statistically, is the over-melting, under-melting is taking place. Those statistical control charts are set with a lower limit and upper limit and center of the data, and then the violations are recorded. So there's no major violation here, but you can see that even with this optimal, the commercial process parameter set, there is some deviations, and sometimes the process goes a little bit off, and that is the time when the defects can occur, like pores, and then you get convection mode, evaporation type of things. Let's look at an example of a digital shadow again, INSTU this time analysis. Now we're going to look at, let's see if I can run this video, okay. Okay, the video doesn't run, right? Okay, never mind. And so we can actually see the spatter analysis in each case, an amount of spatter generated dynamically, record that. And essentially what we're looking here is that, as I mentioned to you, this is a heat energy laser. When it interacts with the powder, it generates a lot of radiation, convection, and conduction. The radiation is picked up, can be picked up by the sensors in actually reflected laser radiation, and then we can actually see the temperature differences. So that's how infrared works in a way. And then we can obtain INSTU thermal video imaging analysis, significant powder particle spatter, and then about 20 to 35% of the powder is spattered. So we should get zero spatter in an ideal situation. Spatter is this particles flying from the melt pool. They are hot. Some of them actually evaporating, but some of them is not evaporating. It's coming back and sticking to the surface and creating a surface roughness. So you do not want, spatter to take place during the process. You can lower the density, you can lower the speed to avoid it, but that requires adaptive control, and it is not happening at the moment. Substantial powder material and heat loss takes place. So let's look at another digital shadow example, INSTU analysis. Again, let me try to run this video if it actually works. Okay, it doesn't work. But we can actually extract heating and cooling rates from the thermal video images. So the thermal videos provide us time-dependent data or time-changing data, and the data changing in time. We can see the heating and cooling rates. You can see that when the laser goes to a location, it heats up and then moves away from it, and then that location begins to cool down. That's when it starts to solidify. And then you can see here also heating rates and the cooling rate. So INSTU, again, thermal video image analysis can quickly give us heating and cooling rates, and they are extracted from those thermal videos. And then we can see a rapid heating from about 600 centigrade to 800 centigrade degree temperature to 1200 to 1400 centigrade with a heating rate of 600 centigrade per millisecond. That is a very rapid heating. And cooling is also taking place with a cooling rate of 150 degrees centigrade per millimeter per milliseconds rather. So you can actually slow the cooling down, and then that would actually provide more anisotropic changes. And so that we could get better, essentially, solidification profile. Now let's look at X2 analysis. This is, every layer is produced and post-process analysis rather, and then we can actually look at the surfaces after the parts are built. This is an example when we looked at it with the focus variation microscopy, and then look at the aerial surface texture. And then surface texture is represented here with the height maps that shows the three-dimensional topography. Now you can see that that topography is quite complicated. When we look at it under the scanning electron microscope, we can see that there is the fused powder, but there is not fully fused powder particles on the surface as well. So when you have another layer of powder coming to the surface, that creates the challenge. We can use machine learning, essentially use the process parameter as input and also the surface texture parameters as output, train the system to predict the surface quality that we can get by changing the process parameters. Here's a predictive model is giving it. So this is a digital shadow because it gets it from the process, but it doesn't provide a feedback to the process. Now let's look at the simulation models. And in this case, we are looking at fluid mechanics, heat transfer, solid mechanics, and metallurgical. And then if we actually use fluid mechanics and heat transfer, we get thermofluid models. And then we can predict all of this, thermal field, Malpol, and Malpol size, Maragoni effect, recoil, etc. If we use heat transfer only through thermal, we can get thermal field, temperature profile, Malpol size. If we use heat transfer and solid mechanics together, we can get thermomechanical models, look at the conduction, convection, phase change, and evaporation. And then, obviously, we can also get plasticity, stress, strain analysis, deformation, and creep. From the metallurgical modeling, we can get thermometallurgical models, and then get solidification, grain growth, grain size, phase fraction, phase transition. If you look at the level of difficulty, this is my understanding of these models, is that most difficult were represented with red, the easiest one represented with blue. And we can use thermal models using ANSYS type, console type simulation packages, or in-house codes, thermofluid models, thermomechanical models, and thermometallurgical models we can use. For new materials, we must develop laser powder bed fusion as much as we want. A need for this experimental data required because that's where we connect the digital model to the physical process. So I think I'm going to skip some of it. So let's look at our vision simulation model towards digital twin. So we have physical based simulation models, we have physical part manufacturing, and we have inputs and outputs, and then we have multi-scale models, Malpol, mesoscale models, layer-wise, part scale model, 3D porosity type models. What we want is to predict the outputs, defects, grain growth, microstructure, stresses and distortion, and optimize process parameters. Here are some examples of those simulation models. This is a model to show processing of powder when the powder particles are modeled. And here's a model that just shows a global model of the 3D build. And here's a model, either cellular automata or kinetic Monte Carlo type microstructure evolution simulations. We also done some simulations by using simply MATLAB. So we had input variables, and then inputs and variables are the fusion parameters, as well as laser parameters and powder properties, generated thermal melting models, liquid Malpol model, and solidification microstructure model, and simply solving by the transfer equation, modeling the phase change between the liquidus and the solidus, and so on. And also laser heat source is modeled here. And then as a result, we get the melt pool. This is only thermal model. We can get its melt pool size and shape, and also thermal profile, as well as rise and fall of the temperatures and the locality, which means what is the time spent above the melting temperature, because that's the time that the heat may be actually transferred into convection and vaporization. It's a simple two-dimensional model that solves for the XY domain and then use this solution to get the solution in the XZ domain. So we have a three-dimensional model as well. In this case, this is also a 2D model. Again, we can get multiple tracks, again, by using MATLAB and solving heat transfer equation, we can get the shape of the melt pool. And it's dynamically changing melt pool, so this shape is not stationary. And then we can also see how this can be affected by the process parameters. Let's get to the thermal solidification model. In this case, we use, again, MATLAB, and we wrote our own code. This time, we solved the heat equation in 3 dimensions, and then we get a 3-dimensional solution for multiple tracks. And then we validate it with the simulation results with the thermal images. And then we use a phase field method to predict the nucleation or solidification along the melt pool boundaries. So this is the actual image from the scanning electron microscopy or actual optical microscopy. And this is the boundary of the melt pool. And the cooling starts from, hot and moves towards the cold space. And then we can see the growth directions. And then in this case, I'm able to run the video now. That's great. So you can actually see the 3-dimensional thermal analysis, and the temperature gradients are extracted from MATLAB, and they're used in the phase field, and then you can see the phase distribution. This is very similar when you have water and you put it in the cold, freezing temperature outside, and water begins to crystallize. So that is very similar. In this case, we're working with Inconel. So it's a multi-material, it's more challenging, but it's the same idea. Now, this tells us what is the time the solidification that takes place, what are the growth directions, and can the process be controlled by changing its parameters. So this is a digital model that needs to actually be intertwined with the physical system. Here's the melt pool boundary and the solidification dendrites moving into the melt pool as the simulation results. Let's talk about directed energy. Do we have time? Like 5-10 minutes?
Yes, we have 10 minutes.
Okay, 10 minutes is enough. Let's look at the directed energy deposition field. In this case, we're interested in wire arc directed energy deposition. So we can do wire arc deposition, wire feedstock, either laser or electron beam wire directed energy deposition, or we can actually do wire arc directed energy deposition. So all three of them have a big advantage over powder bed fusion. Why? You see that the powder bed fusion, you have a powder bed chamber. So the part size is limited by that. You cannot make large aircraft wing structures, for example, 3D printing. You can only do that with this directed energy deposition processes. And that's why they are actually selected. This is an example from Cranfield University in UK. The part is 1.2 meter long. So the problem is, the advantage is the size is not limited. You can actually have large parts built and higher build rates, so much faster than the powder bed fusion. But it's the poor resolution, geometrical resolution, and then the powder bed fusion, and the microstructure is more problemsome than the laser powder bed fusion. And always machining is required. Some people are actually looking at both DED and machining integrated machine tools. One problem is a big problem here. The microstructure is very important for aerospace companies because this process generates mechanical anisotropy in the properties. So in that case, that needs to be remedied. So here comes the method to do that is the grain refinement. We need to control the microstructure during the solidification in wire arc directed energy deposition in order to get a uniform equiax grain structure. So this is a very famous chart. It shows the thermal gradient on x-axis and growth velocity in y-axis. So many traditional manufacturing processes remain in this side because they're not very fast, and they, thermal grain is not that fast and high. So you get equiax dendrites in that case. So you have high cooling rates. But in the case of metal additive manufacturing, laser powder bed fusion, laser powder directed energy deposition, or wire arc additive manufacturing, you are in the boundary. So you may actually end up with columnar dendrites. In that case, huge mechanical anisotropy. So the yield strength or tensile strength in one direction is very low, very high, or just about bulk material in the other direction. So that's a problem because you cannot put a structure in place if there is mechanical anisotropy, mechanical property anisotropy. As well as during the solidification, a number of defects are incurred. So thermal gradients G and high cooling rates T must be optimized to actually bring the dendritic columnar structures to equiax dendritic structures. And so the way to do that is the way to obtain equiax grain is to do grain refinement. So we can actually offer a solution by introducing a solute that promotes constitutional supercooling, or add potent nuclei, or a combination of the two to do the grain refinement during the solidification. So we're working towards that other than the laser powder bed fusion. Again, this fits into our vision of digital twin because input parameters are these, and then we have the physical-based simulation models I will show you just shortly, and physical parts additive manufacturing, we can actually collect sensory measurement data and then address those. So in terms of model for the wire arc DED, we can take the inputs and variables just like laser powder bed fusion, but this time we have different heat source, arc source parameter, and then solve it for the thermal model, and then obtain Melpol model, and then use a solidification microstructure model. This time we use a cellular automata model for the solidification microstructure, and we get number of outputs. And this is the material, which is Ti64, titanium aluminum alloy. So the computational scheme is essentially solving the heat transfer equation, but this time we're using finite difference method. And then we have thermal boundary conditions. And for the solidification model, we are using cellular automata model and using the local thermal history. From this, we are simulating the nucleation and growth. Cellular automata method uses the phase nucleation, whether it's homogeneous or heterogeneous, and formation, and then possibility of phase transformation in a discretization model. So you see that we have the inputs, thermal model, and then we get the liquid Melpol, and then we use cellular automata, and then solidification model. But in each case, from the thermal model, we run a stochastic simulation, evaluate at each node whether it's a solid node or a molten node, and then if it's a molten node, it needs to solidify, come back through the solidification. So then we can actually look at the probability of heterogeneous nucleation and homogeneous nucleation. And in this case, we assume homogeneous nucleation is 0. A purely heterogeneous nucleation follows this probability function, and then this is how we run the simulations. So here you can see during the wire arc directed energy deposition, we're actually processing a thin wall 4 millimeter wide titanium 6-4 geometry, and then we have the temperature profile, and then the print speed is about 1 millimeter per second, and then we have the cooling curves, and then from this we can use it as an input to run our microstructure model. So it's at this point it's just a thermal simulation model. It doesn't actually use thermomechanical type things, like it doesn't calculate stresses, but this thermal model is merged with a metallurgical model in order to see how the solidification will take place. Now, in this simulation, we will add solutes or the nuclei or both in order to see if it actually improves the solidification microstructure. So let's go to the microstructure simulations. All right, so here we have, without having nucleons like solute or nucleophases, we get dendritic structure. So, right, you see the long columnar solidification microstructure. When we start adding some solutes like chromium, and this is just simulation, right? So we didn't do it physically yet. We're just designing this in the simulation platform. And then we obtain 50% of the grain size reduction. So the vinyl microstructure is finer. This is the case 2. It's still columnar, but at least the grain structure is finer. When we start the final microstructure equaxed, if the nucleophase is added, so this is the case 3, so you see that the grains are larger but equaxed. So in that case, we can start to make them smaller, because if we refine the grains, we can improve the strength of the 3D built microstructure. And then this is the case 4, and eventually by looking at the recrystallization and subsequent grain growth, and this is actually coming from the cooling curve, and then we can actually look at the microstructure obvious improvement. So grain growth is essentially based on those local surface energy and grain growth kinetics. And then final microstructure we obtain from case 3 by grain growth and controlled grain refinement. We get very small grains, equaxed grains. So this is what we want to get in all of the directed energy deposition processes, whether it's a powder feedstock or wire feedstock, whether we use laser or wire arc or other energy sources. So this simulation model can be applied to all of these, and then we can control the grain refinement. So these are final remarks. This is a company from Sweden, and they make laser wire directed energy deposition machines. You will be seeing more and more of them. They're better than the wire arc directed energy deposition machines. And grain refinement and tailoring is important in directed energy deposition AM, metal AM processes, because we want to obtain equaxed fine grain microstructure, especially titanium, nickel alloys that go in the aircraft, aerospace applications. And then we can say the growth restricting solute-based grain refinements are the solution to the problem, and then we demonstrated that by adding chromium and some other nucleons. And then by adding those solute-based grain refiners species, we can look into adding different kinds of species like boron, lexaboron, latanium hexaboride, and then we can see that we improve the equax grain structures during the solidification. So this is an area that we're working. So let's just give some conclusions to the entire talk. So you see that for us, we have to provide accurate and representative models, generate new knowledge using in-situ process monitoring, and also create a better understanding and integrated system in metal AM, so that the metal AM becomes a more reliable process group in industry. So we can actually offer different solutions, and we have to understand the physical transformation of the material, and so that the industry can adopt this better. One interesting challenge is to provide a complete online control of the material transformation in real time. And offline metrology is also needed, specifically developed for metal additive manufacturing. A lot of parts with intricate geometries, internal surfaces cannot be measured easily. So computer tomography type of techniques are needed for quality control. And also, as I mentioned, detection of the internal and external defects in the various different sizes of additive manufacturing parts. The quick measuring of all of these defects in-situ, ex-situ are needed. And then obviously coupling those physical defects to the process parameters, also process signatures, so that we can control the parameters and provide improvement to the high quality part production, and also develop closed loop control systems. A lot of times monitoring just stops there. There is little control, so there is also need for control systems. Offline metrology and quality control techniques will definitely improve, and in this, all of this, machine learning can also help. Machine learning can also help validating and optimizing the models that we've seen, thermal model, microstructural model, once they are merged with the physical sensory data. Well, that's it. Thank you very much for listening. I hope this was useful for you, gave you some ideas about research directions in this field. Thank you very much. And I'd be happy to take questions.
Yeah,
yes.
So feel free to ask questions.
Also, thank you for this very exciting talk. You mentioned about the closed loop, right? I also noted that at the beginning you spent quite some time looking at in process monitoring. You know, let's say to mostly using the camera. Have you ever or you or your colleagues have demonstrated that with that process in sensing or monitoring with compensation, right? Later on in you see the improved, at least the surface defects reduction.
Very good question. I didn't talk about that because this would add additional slides and we don't have time. Yes, there are some approaches currently done to control either the laser power or the scan velocity, because those two things can be done very easily. It's electronics. So, but then the loop is not closed. You don't quickly see the effects of those. There is not a technology that's real time, so that you know if you want to implement an adaptive control or feedback control to the system that requires sufficient feedback signals to be used, so that you have an error that goes into controller, then you compensate that. So that's where it lags. Adaptive control is a control where we try to use the onset of parameters are going to about to change things so that we adapt new set of parameters. So all of these are the control techniques beyond monitoring can be applied. There is little research progress in this field. There's lots of people working, but the research progress, let's say in monitoring, simulation modeling, research progress is 70% towards the end goal, let's say. Here, control is about 5–10%. So it's a good opportunity for the ones looking forward for future research. How do you do adaptive control in real time in metal additive manufacturing systems? Yeah.
Thank you for the question. Really good question.
Good question, yes.
Okay, any other questions?
Yes.
Currently, are your defects in this additive manufacturing, are they detected post-process using liquid penetrant or magnetic resonance? And do the defects really come to light after a certain time after the manufacturing, or could they potentially be detected?
So defects are not static. They're taking shape during the process. For example, when keyhole effect takes place, you actually disturb number of previously fabricated layers. They go through processing again. So, and also some of the defects come from thermal stress gradients, like warping, distortions, etc. But a lot of times those defects are identified, as you mentioned, post-process measurements. And it takes really a lot of destructive testing to be able to reveal those defects. Some of the defects, you can see it on the surface, and I showed that at the beginning. But for example, it requires scanning electron microscopy to see the defects, and you cannot do this in the process. So quick measuring techniques are in dire need in order to see layer-wise, not just layer-wise, track processing, as well as once a layer is finished. So a lot of machine tool companies developed a really quick assessment of their layer builds, either by fringe projection, optical tomography, so that they can see what's on the layer. You cannot see what's under the layer. You cannot see what's under the surface. And putting a computing tomography type of device into a powder bed fusion machine, let's say, it's too expensive. Maybe computer tomography would be more expensive than the... So what they do, they actually pick one part out of, let's say, a batch, and then look at its quality, just like the traditional quality control techniques. Like semiconductor industry, they don't really look at every wafer. They have this virtual metrology. They actually use wafer data to create a virtual metrology tool. So same thing, virtual metrology can be done for, in fact, just to come to that, I'm actually collaborating with a professor in WPI, and then we're trying to develop these virtual metrology tools for the additive manufacturing. So if you can predict the onset of those defects to occur, you can mark it, you can record it in the virtual metrology tool, just like it's going to happen. And actually, randomly, stochastically, they're happening, and their sizes can be affected by the laser process parameters. Then they can implement this into the machine as a virtual metrology tool. This is in practice in semiconductor manufacturing. They don't inspect every wafer that they manufacture. So you cannot inspect every layer that you fabricate either. So, it's an open question, open problem. There is no answer to it, but it's a great research opportunity, for example. Yeah, you're welcome. Very good questions. And I know a lot of you are working the different topics, and maybe some of you tangentially related to this. I appreciate the time you spend and listen about this. If you have any other questions, you would like to reach out to me privately, you can reach out to me with an email, and we can set up a Zoom meeting and talk about it. I'd be happy to do that. Thanks to the COVID, we have Zoom, right? Or,
Okay, so
yeah.
I think due to the time, I think
Yes.
we have to wrap up the meeting here, seminar here. Okay. And okay, thanks again to Dr. Özel today's wonderful talk. Okay. Really good summary and really good.
A lot of things to talk about. Yeah, unfortunately, time is small. Yeah,
This is me, Jiang.
nice.
Yeah.
You're Fang, Dr. Fang?
Jiang.
John,
Jiang.
okay, yeah.
So I'll be the next one to meet with you.
Okay, yeah, yeah,
We can go to my office and show you my lab as well.
sure.
It's really, yesterday the weather really good.
Yes.
We get cooled down a little bit.
Really? Oh, okay.
Today is 50 something. Yesterday was 60, 70. You experienced that, right?
Yes, we had a lot of rain yesterday in New Jersey. My flight delayed because of that. It was cold and rainy.
Yeah, here we got very windy.
So you're getting that weather from north, maybe? Okay.
Not that bad. We still have 50s.
Yes.
Actually, next meeting is you.
Yeah, so then after me will be Henry, right?
Yeah, and then we go to the lunch together in the faculty lunch.
Family lunch, okay, yeah.
You're getting another good speaker from Vanderbilt about additive manufacturing as well, right?
Oh, okay.
I saw
Probably
John invited.
Probably, yeah. John is a part of our manufacturing program.
Yes, yes.
You probably know manufacturing here mostly associated with industry engineering. You know that, right? Industrial manufacturing.
Yes, yes.
Your university is probably similar.
Yes. Well, it's changing because they hire a lot of manufacturing people in mechanical department.
Oh, okay.
Now, I would say right now it's 50-50. Of course, that creates competition.
The drop
Is it okay?
That's the way.
Okay, yeah. Oh, wait a minute. I think I should take. I should put it back. I wanted to make sure that, you know, it's not a big.
Turn it off, and then because we have a battery.
Okay.
They just
How do you turn it off? Very nice.
Okay. Let's go. I think, yeah, perfect.
So in industrial engineering, I think some people moved. And they have.
yeah, some retired.
Some